Next, we're going to discuss the analysis of circuits containing dependent sources. So with certain modifications, the analysis tools developed for passive circuits also apply to active circuits as well. Circuit reduction applies to active circuits, but in so doing, we must not eliminate the current variable for a dependent source. Also, we do not turn on or turn off dependent source independently when using Thevenin's theorem or superposition. And I'm going to highlight these differences with examples. In our first example, in terms of analyzing circuits with dependent sources, here we are given an independent current source which is controlling our output circuit here containing a dependent current source, and what we want to do here is find the current, voltage, and power delivered to this 500 ohm output load. So we see here in our dependent current source is controlled by Ix, so we need to solve for that, and we can use current division. So here we have Ix is equal to, using current division, our input is Is, so it's the opposite resistor, 50 ohms, divided by the sum of those two resistors, and that's equal to 50 over 75 Is, and we can simplify that to be 2/3 Is. We can look at the output current I0, and we see that I0, in which we see that Iy is equal to minus 48 Ix, but we'll first express I0 in terms of Iy. So we see that it's the opposite resistor, which is 300 ohms, all over the sum of those two resistors, 300 plus 500 Iy. But we note that Iy is equal to negative 48 Ix. So in this case, we'll simplify this. This is just 3/8 multiplied by minus 48 Ix. But we can substitute Ix in terms of Is, shown here. And we see that negative 48 cancels out with this 8, and we're left with minus 18, since 48 divided by 8 is 6. 6 times 3 is 18, and Ix is 2/3 Is. So remember, this is Ix now. So 18 divided by 3 is 6, and that leaves a minus 12 Is. Okay, minus 12. Let me clean that up a little bit. So that's minus 12 Is. And then we can just use Ohm's law to find VO. VO is equal to IO times 500, but that's equal to minus 12 Is times 500, which yields minus 6,000 Is. So the input and output relationships that we've shown here in terms of this equation for Ix and this equation for VO, where this is VO, shows that we are in the form y equals to kx. Now the proportionality constants are negative because the reference direction for I0 is the opposite of the orientation of the dependent source reference arrow. In other words, the active circuits often produce negative values of K, which means that the input and output signals have opposite algebraic signs that we just shown here. Now circuits for which the constants R negative are said to provide signal inversion. In other words, if I have let's say a sinusoidal signal that looks like this at the input, then at the output it looks just an inverted version of that and possibly amplified. So it's important to keep track of signal inversions. Now, finding the power PO, we just use the simple IV relationship, IO times VO, and that's just equal, when you substitute those values, is 72,000 IS squared, where we substitute VO shown here and substitute IO shown in here. Let me highlight that. There's IO and there's VO. When you take these two equations that are highlighted, we can find our power, and it turns out to be 72,000 IS squared. Since we calculated the power output here, let's calculate the input power given by IS. Now these two resistors are in parallel, so the power at the input, clean that up, power at the input, we'll call it PS, PS is equal to IS times R squared, and that R is defined in this case to be the parallel combination of the 50 ohm and the 20 ohm. That's equal to 50 over 3 IS squared. Now we see that PS has a IS squared term and PO has a IS squared term as well. So therefore the power gain P power gain is equal to the ratio of those two, 72,000 IS squared all over 50 thirds IS squared, and this turns out to be, let me separate that, 4,320. So here the power gain, let me highlight that, is much greater than unity, which means that the circuit delivers more power at its output than it receives from the input source. At first glance, this appears to be a violation of energy conservation, but we have to remember that dependent sources are models of active devices that require an external power supply to operate. That is, the external power supply is not shown in the circuit diagrams, but it's implicit when we do these type of calculations. So when using a dependent source to model an active circuit, we assume that the external supply and the active device itself can handle whatever power is required by the circuit. So when designing the actual circuit, the engineer must be certain that the active device and its power supply operate within their power ratings.